So, okay, we'll continue further with electrostatics. And this is what you see in the screen. There's a circular wire loop of radius r, which has a total current q distributed over its length. So, the total charge q over this entire wire. And if a small length dl of wire is cut off, so this is small piece here, this is equal to length dl, is cut off from here. In that case, what is the electric field at the center due to the remaining piece of the wire? We need to calculate what is the field at this point at the center, and its radius is given as A. Okay. So this case is based on which principle you use. This also, it can come in different form, very common kind of question. And the key point here is the principle of superposition. If at any point, if equal and opposite charges are placed at a point, then field at any point in the space does not change. So what we do here, so here it has some charge per unit length lambda, and that lambda charge per unit length is equal to q divided by 2 pi a. That's the charge lambda it had here. So what we do here, just to, because the symmetry is lost, we don't know what the formulas for the gap is. We add another, we complete this circle here by adding a charge here. So what we do here, we complete this circle. We add a small charge dq, which has same, is identical to the piece which is cut and removed. So we place two charges, one part equal to part which is cut and removed, and other is exactly opposite of that. So we place a charge dq and minus dq, and dq is exactly the same wire which has been cut and removed. So basically what has been, by adding this one, it becomes a full circle which creates a zero field here. The field created will be only due to this minus dq charge. And what is minus dq? Dq equal to, the minus dq charge will be equal to charge per unit length minus lambda charge into per unit length into dl. That's the charge at this point here. So we had total three system, and what is the field at the center? Very easy to calculate. And since this length is small, is field at the center, it can be treated as a point charge. Very small length, so I can treat as a point charge. Field will be equal to k into dq divided by a square. And which direction the field will be? The field, since it's a negative charge, positive charge is field is readily away. Here it is negative charge, field will be directed towards the charge here, negative charge. So this will be, if it is cut here, this will be direction of field created at the center due to the entire ring. It's a ring with a small gap. The charge is distributed over a ring. Calculation of field at any point on the axis of the ring. So this ring is placed in xy plane. Center is at the origin. If I have to find field at any point P, which is lying on the axis of the ring. So if you recall method of calculation, we use symmetry. If you take two small elements on diametrically opposite side, they will create a field. If both ring is charge is positive, they'll create a field DE and DE in the radially away direction. And what we notice here, these two fields, horizontal component will cancel out, or more appropriately, what will happen? The components of field perpendicular to axial direction will cancel out, and along the axis will get added up. So based on then, if we calculate field here, so, and second thing, what we need to understand here, if we divide the ring into several small equal elements, each element will have same component along the axis. Because everywhere angle it is making the axis, all elements are making same angle, they are the same distance. So all dq here, if I take what is their z component they are creating, what is the z component of field created by each one of them? Each one of them will create a z component of field which is constant times the charge is dq divided by square of the distance, and square of the distance will be equal, okay, if this height is h, or sorry, let's call this as z only. So in that case, square of the distance will be equal to r square plus z square. And if I have to take its component, angle theta into cos theta, that becomes that component. And what would cos theta be equal to? Cos theta, so it will make a angle theta. Theta will be, see, if I look at, I think this part, if I look at, theta becomes a little easier to understand. So what is this theta angle is equal to? Cos of this angle. Cos of angle is this divided by inclined distance. This becomes equal to z by root of r square plus g square. And so we can understand that this is axial component. So another way to understand this formula, if you want to keep in mind, if rather than having all this charge dq distributed over the periphery of the circle, if entire charge q is placed here, q, even then the axial component remains same here. Axial component remains same. So I can remember the formula as k into q divided by inclined distance square into cos theta. So basically, I take the total field created by charge q. Resultant is equal to only axial component. So kq by r square, r being the inclined distance into cos theta. Or otherwise, also you can remember formula. I think very often, if this is taken in x-axis, the field on the axis is equal to kq into distance x divided by r square plus x square raised to power 3 by 2. This is a common format. We write this formula. Okay, and that's what we need to keep in mind. And important thing, what we need to understand here, this charge is distributed over circle. If the charge is not distributed over circle, if the charge is, suppose this total charge q, rather than distributing on the circle, if I distribute as two parts, q by 2 and q by 2, if I place q by 2 at two diametrically opposite points, still the field at this point will not change. Similarly, if I distribute this charge in four equal parts, q by q, 4, q by 4, but all four charges are placed at equal distance on the perimeter of the circle, still the field at point P will not change. So as long as I distribute the charge in a symmetrical way such that perpendicular components cancel out, field at point P will remain same. So if I just to give an example, suppose charge is like this. Let me draw a simple figure. And you should understand the reason also why it is so. So in xy plane, let me look from the top. So top we are looking at xy axis. Okay, let me look xy axis, and this is the circle of radius r. It is placed, and we can always this is a hexagon inscribed in the circle. If I place charge q by 6 on all points on the vertices of the hexagon, what is the field it will create at a point equal to z naught? It will create same field as the ring charge. And you should understand the reason also, because all of them are creating same axial component, and they are placed in a such a way the perpendicular component is cancelling out. And at what distance is the field maximum? Field becomes, in case of if it is circular charge, and even it is q by 2 also, the field becomes maximum at a distance r by root 2. And if you recall, what is the field at the center here? If this charge, ring charge, because symmetry, field at the center will be 0. As we go further, field will increase, and infinity it becomes 0. If I need to draw how would field vary as the distance changes, field will vary lengthy like this. So this direction is z-axis, and this direction, if I plot the field here, field is 0 at origin, it will increase, it will become maximum. Which point it will become maximum? When the distance is equal to r by root 2. And if it becomes maximum for circular ring charge, even if it is like a hexagon or equilateral triangle also, it will become maximum at the same distance. It creates identical field as circular ring charge. Then, there are some questions which are just like a simple kinematic question. A charge particle of mass m, 1 kg, and has some charge also. It is thrown from a horizontal ground at an angle theta equal to 45 degree with a speed of 20 meter per second. So far, first part is okay. This is something is a projectile, and u is given and theta is given. So we can draw that part. So this is given, u and theta is given. So this is u, speed of projection, angle is 45 degree. But there's a bit of difference here. This is mass, it also has a charge. Charge q is 2 microcoulomb. And in the space, there's a horizontal electric field. So because of presence of horizontal electric field, in addition to gravitational force, electrostatic force also will act. So this is a general question of, it comes into the category motion of a charged particle under a uniform field. If field is uniform here, it will exert a constant force. Which direction? In this case also, if the field is acting in this direction, the force also will act
Okay.
in this direction. So again, how do we analyze this motion? See, in case of gravitational motion, if this were moving only under gravity, it would have moved like a parabolic path, and this is kind of path it would have taken. And in case of gravitational, but now because of this force, there is an additional force and hence acceleration acting in the x direction. So its motion may be a little more difficult, but a little more complicated. It may have something like this. So what we need to calculate, find the range. This question is more of a kinematic question. How do we find range of a projectile? Any 2D motion, first point is we split into two 1D motion. In case of along x-axis, what is happening? In case of x-axis, it has some initial velocity which is equal to okay. In this case, it will go back and right. It is u is 20 meter per second. So ux is equal to 10 root 2 meter per second. But in addition to initial velocity, it will also have an acceleration. What is the acceleration it has? For force by mass, it will be equal to QE by m. So that will be the acceleration it will have. So if I find this acceleration here, we can easily find this acceleration that will be equal to 2 into 10 to power minus 6 is the charge, into 2 into 10 to power 7 is the field, and mass is 1 kg, and that comes equal to 40 meter per second square. Oh, it's 4 times g. That's the acceleration. So, and what is happening in y-axis? Y-axis, there's absolutely no change. Uy is equal to, again, 10 root 2 meter per second, and ay is equal to minus 10. How do I calculate range here? If you understand the range here, see, will the time of flight of this particle change? See, time of flight is only dependent on motion along y-axis. So time of flight will not change. What would the time of flight be? Time of flight is equal to 2 into uy by ay, which will be equal to, okay, if I put those values, it will be 2 root 2 seconds. So time of flight is 2 root 2 seconds. So what is my range? Range is equal to displacement along x-axis in time t to 2 root 2 seconds. So displacement along x-axis in time t is equal to 2 root 2. So what is the range I will calculate here? I will calculate the range will be equal to ux into t plus 1 by 2 into ax into t square. So if I put those values, I can easily find this range here. So all such question, wherever there's a uniform field, is simple kinematic question. There's additional acceleration we take in account and we solve. There's some question about, okay, this is an SHM, a bob of simple pendulum mass. It has positive charge, is oscillating with time period T1. If electric field intensity is applied vertically upward, what will be the new time period? So let's understand here oscillation of any particle here. See, first, let's say this first requires understand of basic oscillation property. So if you have mass m, which is oscillating like a pendulum, see, what we need to understand here, in case of pendulum, there's one, of course, two forces acting. One is gravitational force. And what is the characteristics of gravitational force here? Characteristics of gravitational force is something which is constant in direction as well as magnitude. And the restoring force is created by component of gravitational force towards the mean position. So its component creates this kind of position. So as well, so and effectively this is a force which is acting. And its variation can come in multiple forms. Let's look at if this particle, in addition to mass, it also has a charge. It has a positive charge, and there is an electric field of intensity vertically upward direction. How is E acting? E is acting in the vertical direction. So what happens in addition to mg? Now one more force is started acting. What is the force is started acting? QE. And first of all, of course, QE has to be smaller. Otherwise, is oscillation will very different nature. So if I have to calculate here, so what I notice, this QE also has is similar to gravitation. as far as pendulum goes. You know why is it similar? Just like gravitational force, this also does not change magnitude, does not change direction. So effectively, so what has happened if I want to do in a short fashion? See, if I take in terms of component also, what will happen? Mg will have a component, restraint component, QE will have in the opposite direction. So if I understand what change has taken place here, and this valid in any cases earlier, we are not taking tension force. I'm just looking at the force which is creating component along perpendicular direction. So earlier, the force which was having component along towards the mean position or along the perpendicular direction, earlier the force was mg. Now, because of this force, the force becomes equal to mg minus qe. So here, if this was the force, I used to take corresponding value of g. So what is g effective whenever such constant force acts? I can take g effective as the net force which is acting divided by mass. So what would be G effective in this case? G effective becomes equal to mg minus QE by m. Or so what will be the time period? Time period equal to 2 pi root L by G dash. So I'll write time period is 2 pi root L by mg minus QE into m. Okay. So that's what the change will happen here. And somebody is interested. What happens is Q is equal to 2 mg. Can anyone think of, anybody tell me what will happen is Q is equal to 2 mg? What will be the new time period? Answer is very simple. What will happen if Q is equal to 2 mg? Can anyone think of what will Q equal to 2 mg? If Q is equal to 2 mg, it will oscillate not like about mean position, it will oscillate like this. It will oscillate vertically above point of suspension. And when it oscillates above a particular point of suspension, also net force is equal to mg, it will have same time period as before. So if Q is becomes equal to 2 mg, same time period, but rather for oscillating below the point of suspension, it will oscillate vertically above the point of suspension. And this kind of thing, so this is one type of thing. So you understood this part. I'll just mention one more point here. I mentioned last time as well, and I said sometime we forget here. See, this is one type of question. The second variation of the question may come. This charge is Q here. If at the point of suspension also there is charge Q here, if I place a charge Q here, will the time period change? See, in this case, there's a difference between this case and this case here. In this particular case here, the force which is acting, the electrostatic force here it is in this direction. When the mass reaches this point, electrostatic force is acting again in the radial direction. It doesn't have any perpendicular component. Since it does not have same property as the gravitational force, its direction is not the same, and its direction is always along the string, and it will not have restoring component. This will not alter the time period. So when two masses, if you place a charge at point of suspension, and particle also has some charge, in that case, time period remains same. But if we create an external field, yes, time period will change. And another variation of the question could be if E is equal to horizontal direction. If field is in the horizontal direction, what will happen? So suppose E is in the horizontal direction such that Q is equal to mg. What will be the time period? Can you all visualize if Q is equal to mg? What will be, so what are the forces acting? Two forces will be acting, mg as well as QE. So what would be the mean position if E is horizontal? We have done similar question. A similar question can be done also in case of pseudo force. It is also valid. Similar thing is applicable for what are things it is applicable for? Okay, let me finish this part here. So what would be the mean position if Q is also acting? Mean position will be something like this. Mean position will be when mg and QE. Mean position will be at angle of 45 degree from the horizontal. This will be the mean position. And if I have to calculate here, what is the net force acting in this case when this is selected? Net force becomes here we taken mg minus QE since the vector quantity. It becomes equal to mg square plus QE square. And hence G effective becomes equal to F net force divided by M. And I'll calculate time period. So that also can be calculated. So when are we the cases we can use this effective force? One we have taken whichever force has property something similar to gravity, which remains constant in magnitude and direction also does not change. So what are the cases which come to our mind? Any force with constant magnitude and directions like gravitational force can be treated as equivalent to gravitational force for pendulum. Force of buoyancy comes into the same category. Pseudo forces also when point of suspension comes into same category. Electric field also comes into the same category. All such question we can do same. Yes.
So in this case, the G effective that we get, it's not in like in the same direction as G, right, sir?
Which case?
When there's a horizontal field.
Yeah, that's why I said also. It is not in the same direction. So which is the mean position? That's a,
Oh, okay.
it will oscillate like this.
Okay. With respect to the mean position,
With respect to
it is
mean
going.
position.
Yes.
It will also oscillate with respect to the mean position. And we can do it step by step also. We find out mean position. See, had we done step by step, how would I have solved this question? I would have first found the mean position, and then I'll give small displacement. And when I give small displacement, again I take the component in the perpendicular direction. If I do so, again I get the same result. Okay. And then is flux, the electric field. But how do we calculate flux? I hope all of you recall. Flux is very simple thing. It's about a dot product of field and area vector. And you have taken if field is not uniform, we can divide it into small area. If field is uniform and surface is plane, if field is uniform and surface is plane, we can take as E dot delta A. E dot delta A is when surface is plane and field is uniform, and we have taken some projection and all also. So let's understand here, if field in the space is given like this, magnitude of E naught is given, what is the flux of this field through a circular area of radius 0.02 meter, the radius parallel to YZ plane. So if I have to use this particular formula here, E is already given in vector notation. Even area vector also I need to write. So what is the area vector? Area vector is taken up, direction of area vector is perpendicular to the plane. Since area is circle is in YZ plane, its area vector can be taken as plus I cap or minus I cap. So any open surface, there's no unique way of defining. I could have written area vector as 0.02 I cap. It is also valid to write as 0.02 minus 0.02 I cap. For open surface, both areas are possible. Only when it is closed surface, then we take outward normal as positive. So if it is see, if we just recap this part here. So if I have an area which is something like this, if I have a square area vector is normal to the area surface. This also can be taken as a direction of area vector. This also can be taken as direction of area vector. But if I complete a box here, if I make a complete box here, it becomes a closed surface. Moment it is a closed surface, and especially when I want to use it for application of Gauss law. In case of Gauss law, there's a yes, this is towards inside, this is outwards. In case of application of Gauss law, which is taken as the direction of area vector, outward normal. So this is the right one. In case of closed surface, this is not the area vector direction. So these are two things we need to keep in mind. Rest all is dot product. Very simple. Okay. Next question. A cone of radius r height is located in a uniform electric field parallel to space. What is electric flux entering the cone? So how do we solve such question? It's a uniform field. If cone is placed, you visualize. So we said, how do we can? Okay, so this is a kind of cone which is placed, and it's a right circular cone. So any surface, what we need to calculate here, if field is uniform here, from Gauss law application, we understand if field is uniform, if I take cone as a Gaussian surface, closed surface, net flux to the cone will be zero. Net flux, because field is uniform. In case of uniform field, there's no charge inside the cone. That's why field lines are not terminating, not starting. So net flux is zero. So other way of saying, flux entering is equal to flux leaving. So if it is kept in horizontal surface, what is the flux entering this one? So entering this, if we have to calculate flux entering the cone, we can also visualize its projection like a shadow. So if there's a parallel beam of light coming from long distance, then only becomes parallel. If beam of light is perpendicular to axis of the cone or it is parallel to base of the cone, the cone will form a triangular shadow. The triangular shadow indicates the light which has been stopped, which has fallen onto the cone. That's why it has been stopped here. So entering area, what is the area on which it is incident? Area on which light is incident is equal to area of shadow it would have formed on a wall which is perpendicular to travel of light direction, which will be a triangle. It will form a triangle of base equal to 2r, height is equal to height of cone. Similar way, if the light had been vertically downwards, if the light is along the axis or field is along the axis of the cone, in that case, what is the flux entering the surface of the cone? Flux entering the surface of the cone is equal to the net flux is zero. Flux entering to the cone, entire surface of the cone is equal to flux leaving to the circle, which is nothing but projection of the uh, inclined surface of the cone on a horizontal surface. So yeah, if field was vertical, flux entering would have been E into pi r square. If it is horizontal, it is a triangular area. So just recap of some of the basic points. This question, just look at the question. So this also first thing what I noticed, electric field is a uniform electric field. What is the flux through the shaded area? So this is a question which is come in JEE Advanced, and those who are little smart, they can visualize what this area mean. So if this area is something what is given here, this area is part of a cube here. So if I draw, since all sides are given in terms of A, if I draw a cube of side A, this is the point corresponding to the side. So what is this area? That this shaded area is the area here. And how is the field here? Field is in this direction, E naught x. This is the field here. So to find flux through this shaded area, if field is along x direction, I can take the projection of the area in on YZ plane. Projection of this area on the YZ plane is in square. Hence, the flux would be equal to E naught into A square. That's one way to understand. What are the other way to understand? If I have to find flux through this shaded area, if I have to use to find flux, if I want to use Gauss law, I have to make a closed surface. How do I make a closed surface? See that how do we make a closed surface with this? So that I can apply Gauss law here. So to form a closed surface, this is one surface. I include this surface also, this triangular surface here. This triangular surface is parallel to xz plane. Other side also this triangular surface, which is also parallel to xz plane. And then I use even the top surface also, and this back surface. If all the surface I include here, two triangles and top surface and back surface, entire put together, everything forms a closed surface. I can apply Gauss law. Net flux to this closed surface is zero. Net flux is equal to zero. If net flux is zero, it means some surface flux must be negative, some surface flux must be positive. Out of how many surfaces are there? Two triangular surfaces. Flux through these triangular surfaces are zero because their normal are along k cap. You understand? So these two triangular surfaces are parallel to xz plane. So flux through this surface also zero. Flux through this surface also zero. Flux through top surface also zero. Flux is non-zero only through one through this inclined plane, and other is through this square plane here. This itself tell you the flux through inclined plane has to be same in terms of magnitude as flux through this square plane, which is vertical. So that's the way we can calculate flux through a shaded area. And you understand, I hope, the idea about the projection and all also, how to take projection and how to even use Gauss law to find flux by completing a closed surface. Some cases on symmetry. And a variation of this question also is common. So let's understand Gauss law application. So there is a charge Q placed at the center of a cubical box of side L. So there's a cube of side L, and this we are right at the center. So we have to visualize this as a 3-dimension. So when we place a charge Q here, uh, what are the various, what we can find flux through different parts of the surface of the cube using Gauss law. Let's see what are the conclusions we can draw using Gauss law. So what just to remind you, some of you, what the Gauss law is. Gauss law says this is something, it says something like this. What does this mean here? This term is electric field flux over a closed surface called a Gaussian surface. So you have to have take a closed surface, then only it is valid. It's equal to electric field flux through a closed surface due to all charges present in the space is equal to charge enclosed. So when you are calculating field due to all charges into class enclosed by epsilon naught. So when we come to this case also, so we take the 6 surfaces of the cube. So flux through all 6 surfaces put together. If I calculate phi here, flux through all 6 surfaces put together is equal to charge enclosed by epsilon naught. This is what I have done. It will be Q by epsilon naught. But since this charge is placed at the right at the center, because of symmetry, each surface will have same flux passing through. So flux through each face of the cube. So flux through each face, because of symmetry, will be 1/6 of the total. Each face will be equal to, because symmetry, will be 1/6 of the total. So it becomes equal to 1/6 Q by epsilon naught. So which basically means, suppose I just consider this square face here. This is a square of side L. And if I ignore all other 6 surfaces, there's a charge Q placed vertically above its center, perpendicular to center at a distance equal to L by 2. So if I just take a square surface, if a charge Q is placed at a distance of L by 2, perpendicular to center and one side, flux is equal to Q by 6 epsilon naught. So we understood this part also. Now, if I take this entire surface, flux is equal to 1/6 of the total flux. Now I took, because symmetry, let's continue how long we can extend symmetry here. Now, if I consider only this part of the 1/4 of this surface, if I take here, are these not, I can divide this entire bottom square into 4 identical squares. This square, and all have identical orientation with reference to charge. Their position is identical with reference to charge here. So each one of them is likely to have equal, or actually will have equal flux. So flux through each of this part here, the dotted part we have drawn, will be 1/4 of this. So flux through this 1/4 of 1/6, it becomes 1/24 Q by epsilon naught. Let's understand what is this square mean. So if I take this square, let me call L by 2 as A. So if I just consider it separately, how is the charge placed with reference to this square here? I can, if I draw it separately, it is something like this. There's a square. Of, if side is A here, where is the charge placed? It is charge placed if I take one of the corner, and if I take a direction perpendicular plane square, and this should be equal to A. So if a charge Q is placed at a height of A equal to above one of its corner, then flux through this square surface will be equal to Q by 24 epsilon naught. And we can even make it as a triangle also. It will become 1/28. So they can extend that logic also. So that way we can take symmetry. So we can continue like that with 1/48 if it is a triangle. And triangle also need to understand here. This triangle, what kind of triangle? If I look from the top, what the triangular shape will be? If I, whichever triangle I'm talking about, triangular shape will be something like this. Uh, in original dimension, this was L by 2. This also L by 2. This is a triangle L by 2, L by 2. I'm looking on the top. And where's the charge placed in this triangle? Charge is placed above. Yeah, so these two sides are equal vertically above this point. At what distance? At a height of L by 2. If I plate a height of L by 2 above one of these two vertices, not above this, not above this. It is about this point or this point. That will be Q by 48 epsilon naught. One more variation of this, if there's a cube here, this cube also, how many cubes I can form of side L by 2 here? I can form L by 2, actually volume becomes 1/8. So we can form 8 cubes here. And how are those 8 cubes? If I take this as a square here, if I basically can form like this, this is nothing. What is this cube equal to? This is okay. So I have completed a cube over a square which is 1/4 of the total square area. So this cube is of side how much? This cube side is L by 2. Now this cube, where is the charge placed? For this cube, the charge is placed at its corner. And when the charge is placed at the corner, do we know what is the flux through this surface here? We know what is the flux here. Flux through this surface is equal to Q by 6 epsilon naught. So if this surface flux is Q by 6 epsilon naught, just tell me what is the flux through this surface here. This surface also is symmetrical to the one at the bottom. This surface, and the bottom surface. All three are symmetrical. All three will have a flux equal to Q by how much? Each surface will have how much flux here? See, this itself equal to flux of this, which is Q by 24. So it will have flux Q by 24 epsilon naught. So I can say if there's a cube here, whatever is dimension, if charge is placed at one corner of the cube, there are three surfaces which will have zero flux, and there are three surfaces which will have equal flux. If I place at this charge, the three surfaces formed by these three sides which are passing through the point where the charge is placed. Other than the three sides, all other three sides will have a flux Q by 24 epsilon naught, charge placed at the corner. So these are very simple ones, easy ones, you need to remember. Okay. Then we come to application of, okay, one was application of Gauss law only. This is a typical atomic model. So nuclear is a beryllium atom. Nucleus has 4 protons. So this has a charge of plus 4e here, and has 4 neutrons. Is confined to a small radius. So this is the radius of a nucleus is given here. It has two 1s electrons. So it will have first orbit and second orbit. In essence, what they are saying, there are 2 electrons in the first orbit, minus 2e, and 2 1s electron make a spherical cloud at an average distance of 1.3. So this average distance is nothing but radius here. So this is inner first orbit radius, r1, and there are 2s electrons making another spherical cloud at an average distance of, you notice here, this is 4 times. And this is typically what we come across in case of atomic model. In case of hydrogen atom also, as per the Bohr's model, the next radius 4 times the first radius. This is R2. So this is how the charge distribution is. And if we need to find field at any point at a particular given distance from the center, we should be easily able to find field. So suppose I ask you, what is the field at a distance r is equal to r1 by 2? What is the field at a distance? Half the radius, first orbital radius, the field will be equal to, in that case, field will be only due to the charge. So if I draw a Gaussian surface here at r1 by 2, this is a Gaussian surface, and because symmetry field everywhere on the surface is same. So if I write flux every time field is same and perpendicular to surface, the flux through that surface will be equal to surface area into field. Surface area is 4 pi r square into field at that distance is equal to charge enclosed by epsilon naught. So if I take that radius, charge enclosed is only 4e. So if I take r1 by 2, I can find that field. If I have to find what is the field at a distance of 2r1, r2 is equal to 4r1. What would field be here at 2r1? Charge enclosed will be equal to plus 2e. So when you have to find at 2r1, charge enclosed will be equal. So if I write the field here, E equal to 2r1 will be equal to k times the charge enclosed is equal to plus 2e divided by square of the distance 2r1 square. So any point just inside, just outside, anywhere we can calculate field. Just inside the 1s cloud, just inside the 1s cloud, what will the field here? Just inside the 1s cloud, the field will be equal to E at R1 minus dr, just inside. The field will be equal to, in that case, charge enclosed is 4E, field will be equal to K into 4E divided by R1 square. So this is pretty simple. It's simple application of Gauss law. We can easily calculate. So I'll stop here. Anyway, my throat is not okay today. So having